Hello, everybody, and welcome to another wonderful day of physical chemistry. So, today we're going to be taking our knowledge of a simple vibrational system, and we're going to be trying to apply our new set of selection rules. So, one of the first things to keep in mind is that in order for a vibration to be excited by a photonic absorption, so in other words, in order for me to have a vibrational spectra, my vibrational state must result in the change of the dipole of a molecule. Now, this is actually a fairly important and kind of revolutionary idea. So, in order for the system to actually absorb a photon, really what's happening is that photon has to be interacting with an oscillating electric field, meaning that dipole or that partially charged has to be moving. If it stays stationary, well, I'm not going to absorb an oscillating wave because there is no change. Now, this actually has some really interesting implications as to which molecules can actually undergo vibrational spectra. So, if I've got a diatomic molecule like H2, this actually won't absorb a photon to undergo a change in vibrational state because it turns out that the molecule has to be polar, because if it's nonpolar, there's nothing for the to absorb the photon. It's nonpolar as is, it vibrates more, it's still nonpolar. So this is what's called an infrared silent molecule. I shoot it with an infrared beam, I see nothing. However, if I have something like hydrogen fluoride, well, it's got a nice dipole. And so I hit it with a photon, and then it starts vibrating faster, and this dipole moves. That charge becomes more or less separated. So, this is going to be one of the most important gross selection rules for vibrational spectra. Molecule has to change dipole when I vibrate. And we'll play around with this a lot more next time. But we also have a specific selection rule we have to focus in on. And in this case, it's going to be the fact that the vibrational state has to change in order for me to absorb a photon and actually see anything. I should have a change in energy level, and this makes sense because otherwise there's no spectra. And due to the nature of uh, the symmetry and orthonormality of the system, at least when we're using a harmonic oscillator, I can't change more than one state at a time. And we'll see how this gets relaxed a little bit later. So if I'm going to absorb a photon, well, I can't decrease in vibrational energy levels because that means I'll be releasing energy. So for simple infrared spectroscopy, my change in vibrational states has to be an increase of one. And so, using this knowledge, we can find the energy of excitation using the harmonic oscillator. So, using the harmonic oscillator, we can go ahead and find the difference in energy in between the V and the V plus one state. We'll refer to this as the V half. So, if I'm going for 0 to 1, this is the change in energy of the one half. If I'm going from 2 to 3, it'd be two halves. But as long as the harmonic oscillator holds, the difference in my energy levels is, well, just the vibrational constant, which, as a reminder, is going to be controlled by the force constant, width of the well, and the reduced mass. We see no dependency on the initial vibrational state. Whatever the V is, I'm always going to have this same separation. However, we do know that this is untrue. And the reason why is because I really should be taking into account anharmonicity. So if I use my anharmonicity or my second order equation, truncation of the Morse potential, we find we have a little bit more advanced of a equation for the differences in energies. So I have my vibrational constant, but I also have this correction term where it's minus twice the vibrational state plus one times the anharmonicity. So it is worth noting that this means the anharmonicity will play a role even if I'm exciting out of the ground state. So one of the things to make note of is that even if you're in the ground, you should account for the anharmonicity. However, by the nature of this equation, and usually the great magnitude of the well depth, this effect is fairly small for low vibrational states. However, it is worth noting as I get to higher and higher vibrational states, what I'm going to see is all of these energy levels becoming much more tightly packed, as the anharmonicity is going to drive everybody closer and closer together until they're practically all degenerate. So, in truth, we tend to think of a IR spectra as one single peak the focused in on the vibrational constant. In truth, what we would actually expect to see is multiple peaks. However, as I'm going to have one big peak at uh, just below the vibrational constant, and then I'll have several slightly smaller peaks trailing off to slightly smaller wave numbers. And the reason why is because most of my molecules will be at the ground state, and we may see a couple at increasingly higher vibrational states. Each one moving slightly to lower energy separations, so will be caught at slightly to the right in a infrared spectra. And with decreasing amplitudes, as fewer molecules will be starting from that state. However, one of the other interesting things that happens when we actually apply anharmonicity and the Morse potential instead of the harmonic oscillator is our selection rule changes. So as soon as we include anharmonicity, we start to see additional overtones that appear. And so overtones are essentially transitions that go more than, that have a change of vibrational state of more than one. So 0 to 3 or 0 to 2. So let's go ahead and focus on the 0 to 2. This is essentially called the first overtone, as it's the first excited state. And it is worth noting most of the overtones we're going to be paying attention to here, we tend to pay attention to come from this vibrational ground state because it is the most highly occupied. And since this is the first one that appears, thus first overtone. Now we can determine the energy at which the wave number at which this first overtone would appear by taking the difference in between our starting state and the one twice as high. So the first thing you'll notice is that the energy difference for an overtone is literally twice as high. So let's say if I'm examining a spectra from 0 to 3000, I see a peak at 2000 wave numbers. Well, I won't actually see the second overtone because it's going to be approximately at 4000 wave numbers off the spectra. So in general, if you're going to use overtones, you have to first start by looking for them. Then one of the other things that you'll make note of is that these overtones will start becoming much more visible, as in they're going to move more into our field of vision as we get to higher vibrational states, as the tendency for the vibrational states that come together becomes that much more amplified when you're not jumping from 0 to 1 state, but you're jumping from 2. So the anharmonicity has more room to play a role. That said, one of the biggest reasons why you tend not to see a lot of overtones, even if I'm looking at a peak that occurs at 1000 inverse centimeters, is because accompanied with this is the fact that they have very reduced amplitudes. So this is one of the important features, is that the 0 to 2 transition is still classically forbidden. Now, when I go to a non-quadratic potential, I can start to see little bits of this transition, as they're not going to be as orthogonal as they would be from the simpler model. But there's still not exactly a lot of overlap in between these two wave functions. So as a good general rule, expect your overtone to be about 1/10 the intensity of the original signal. So you can often find them, but you do have to start by looking for them. That said, if you do find them, they will help provide a lot more information about the anharmonicity of the system, because you're going to be able to see states that are far higher in the potential well than from a typical transition. However, as we've seen before, one of the other tricks that we can do with vibrational spectra is make use of the fact that any type of spectra is going to couple with every other type of spectra that has a lower energy. So in practice, our vibrational excitations do couple with our rotational motion. And one of the other things we can make use of is we see a similar set of selection rules apply for both systems. So one of the first things to make note of is our system will still mostly be located in the vibrational ground state. So most of the excitations we're going to be looking for are going to be going from the ground vibrational ground state to the first excited state. However, we are going to be seeing some changes in our J state or rotational states that accompany with it. And we split this into three branches. First, the R branch. So this is going to be states where our vibrational and our rotational uh, states go up. So consequently, we'd expect these to occur at slightly higher frequencies, as I need the energy it takes for me to naturally jump up, plus that extra little bump to jump a rotational state as well. So this can simply be given by the vibrational excitation plus the rotational excitation. It is worth noting, you'll notice we don't see any anharmonicity, so we are assuming the harmonic oscillator. This should be a fairly safe assumption if we're mostly exciting out of the ground state. The Q branch is a little bit more interesting because the Q branch assumes that we're going to increase the vibrational energy level, but we'll see no change in the rotational state. Now, one of the problems with trying to conduct this excitation is that turns out my photon still has spin, it still has angular momentum. So this is only going to be possible for a select set of systems where we see an change in the electronic angular momentum. These are actually fairly uncommon, but we'll spend a little bit of time talking about them uh, later as we go on to electronic spectroscopy. But generally, the Q branch is seen as forbidden for most molecules. So we also have the P branch, where the vibrational state goes up, but the rotational state goes down. And this is going to have a separation of the vibrational state with a little bit lower in energy because I'm stealing from my rotational state as I'm dropping levels. When we couple these together, we should be able to get a lot of information about both vibrational and rotational motion. It is worth noting that all gas phase molecules will contain this rot-vibe coupling. However, we only tend to really be able to see it for with molecules with a fairly low reduced mass. Because remember, as a reduced mass increases, our rotational constant is going to go from, say, 10 inverse centimeters, which I can see on a typical IR spectra, to something more like half, a tenth, a hundredth of an inverse centimeter, which means the whole spectra kind of comes together into a single peak and it all blends together. So this is something to keep in mind. Also, as soon as we go to condensed media like liquids or solids, well, then all of this kind of blends together because our rotational motion is kind of blocked as the molecules keep hitting each other. There are methods to treat this, but let's just say it's a little bit messy. And that kind of brings us to an important point. So far, we've just been talking about vibrational motion for a diatomic molecule. So next time, we're actually going to talk about polyatomics. Till then, take care.